live.
Hi, everyone, and welcome to another night of Astronomy on Tap Kingston. So where has the time gone? I think we were last with you back in January, although maybe you've been able to join us for some of our other events. I'm not sure I've left these four walls in the meantime, so days are just kind of blurred together. So given all that, a big thank you to all of you tuning in to join us to leave the world behind for some of an out of this world evening. I'm Mark Richardson. I'm the Education and Outreach Officer at the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. The McDonald Institute is a collection of scientists, universities, and research labs across Canada, uncovering some of the biggest mysteries of the universe, and we'll hear about some of them today. But we do this by looking at some of the smallest things in the universe. So I'm here, not on Mars as much as I wish I could, but we do have our proxies doing the job for us there. Instead, I'm here at Kingston, Ontario. Personally, I'm an astrophysicist by training who studies how galaxies form and change over time. And I'm so excited to hear from the different visitors that we have joining us today. They're going to be taking us on a tour of how dark matter is found between galaxies, how lasers let us learn about the cosmos, and maybe how the universe itself might end. And so overall, I just love these kind of opportunities. I love these evenings to be able to spend them with you, really just sharing this kind of wealth of astronomy and astroparticle physics. These events are opportunities to share with you amazing and exciting and useful science in how useful it is in overcoming some of the big problems today. And so I'm so happy that even during COVID, we're able to have these events and people are joining in live or after the fact for those joining in. So hello to everyone joining from home, whatever lands you call home. For me, home is the lands of the Cataraqui. This is now Kingston. It's the traditional land of the Anishinaabe and the Haudenosaunee peoples, and many indigenous peoples before them. And I'm truly appreciative that we were all able to learn tonight from our respective lands. Personally, as a settler from Halifax, Nova Scotia, the traditional land of the Skin Dressers district of the Mi'kmaq, I recognize that my ancestors were complicit when these peoples had their access to these lands removed. And as an astronomer, someone who revels in really the wonder of the land, the planet, the skies, and the universe above, I recognize that this science in particular does rely on facilities that use traditional and sacred lands of various indigenous peoples. Peoples who do have a voice to add to the science and who should be gatekeepers to these spaces. And so I reflect on these things as they're aspects of my identity and how they afforded me certain privileges in my academic life. And so to all of you, I urge you to think of the connection that you personally have with the land around you and the gift that we all have to learn wherever we are. I also encourage you after tonight's event to explore the website whose.land, WHOSE.land, and learn about the past peoples who have lived where you live today. So moving forward from this event, let's reflect and work towards the decolonization of these spaces to make them ones of friendship, love, and access for all those in our community. Okay, so the plan for tonight is simple. It's meant to be a conversation. Astronomy on Tap is all about coming together about the kind of joint interest in the cosmos around us. And so it's meant to be a conversation more than a lecture. So I hope you guys are engaging with the comment section. This is best achieved if you're not zoomed in on the full screen of YouTube. Instead, have it exited out so you have the comments in the sidebar and you can answer some of the questions that we might ask of you this evening. And of course, feel free to grab a drink. I said I'm from Halifax, and tonight I actually have an Alexander Keith's red. Shout out to David Clark, my old supervisor that introduced me to it. But with your drink, maybe open up your mind as well and imaginations. Say hello from the comment section and drop a question whenever you have one. I'll be trying to mediate that conversation between the comment section and our speakers. And so the speakers tonight, we're going to hear from 3 astronomers and physicists who all do very exciting but different research. We'll also have a bit of trivia to break up the engagements, and we'll have some of our usual prizes. And we'll see if we can maybe even find out who the winners are tonight. So do bear with us as we try to figure that out. So yeah, but before we get the ball rolling, I always like to highlight a few things. First, so our speakers tonight I already mentioned, but I want to highlight many of the sponsors that we have for the Kingston Astronomy on Tap. This includes the McDonald Institute and Royal Astronomical Society of Canada, and a number of other locations here in Kingston that provide prizes when we're here in person. On top of that, I realized that it's been like, 4 months since we were last together. So there has to have been some exciting space news or news from space. And more so than just the fact that the Russians or the Soviets have landed on the moon, at least in an alternate history, an alternate news space, if you've been watching the For All Mankind show. And instead, we're going to focus on real life space news, although the second season ended For All Mankind, so I recommend you check it out. But we've been revisiting a common story for the last, now, I think it's been 10 months since we last kind of talked about this. And that is that last summer, and then in January, we revisited this, that the Perseverance rover launched on its way to Mars. This is back, I think, last July. It then had its exciting landing in February. We did a live viewing of this with a panel of experts. We had the Queen's Observatory involved in managing that panel. And it was a really, really exciting event. I hope some of you joined us and had a lot of fun. And as exciting as it was, I think the most exciting aspects of this news is, of course, the amazing videos that NASA has shared since the landing of the actual landing itself. So I'd be remiss if I didn't share some of these with you this evening. Maybe it's worth just sharing some of the audio because they're
seeing significant deceleration in the velocity. Our current velocity is.
So this is that parachute that had to land, first open up so that it slowed down as it went into the atmosphere, and then released its heat shield that it used to slow down on the atmosphere, and then come into the planet itself, and you see its descent. This is a live view from Perseverance rover. This is crazy.
Their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the.
And of course, eventually it had to land itself, and this was through this complicated sky crane maneuver. And they have video of even that, not just from the rover itself as it kind of scoped out where it wants to land. It had video from the sky crane craft as well, so they give us a full view of that whole process. And you can see the jets pushing out the dirt on the ground as the sky crane deploys. Man, this was so exciting during the actual event. I get excited again just watching it. Unfortunately, the cable releases. This is an important step. Otherwise, that crane would just drag the rover with it. And we had a confirmed touchdown, and everybody was quite keen about it. Okay, so Perseverance landed. This was a big deal. NASA has a great track record for successfully landing rovers on Mars, but Perseverance was a little bit unique. It had on board with it a little partner robot, and this was Ingenuity. And so this is this little helicopter. It landed with Perseverance, and it's there to test out basically the technology of being able to use a helicopter in the very thin atmosphere of Mars. The atmosphere of Mars is about 160 times thinner than on Earth. So obviously the rovers have to spin a lot faster to get the same amount of lift. And so in the middle of April, NASA was able to test this out. They did a number of tests, and they've had footage from all of these because it's just so cool to be able to watch this stuff in live action. But I'm going to play you a video of one of these sessions, and it actually has recorded sound on Perseverance of the event. This is the first time ever they've really recorded sound on the surface of a planet, and they weren't even sure if they were going to be able to hear the helicopter as it went. And it's quite quiet, but we'll see if you can hear it at home. So that's the wind that you hear right now. And here's the helicopter right here. Do you hear it? You should hear like a pulsing. course, this is just testing the technology now, but this has a lot of possible prospects, and being able to scout out cool areas, maybe for a future rover landing. One of Perseverance's main scientific missions is to get a sample and prep it for a Mars return mission, which will collect that sample and bring it back to Earth. Having drones like this being able to fly on Mars would allow us to do much better kind of survey of the topology and find those perfect samples for doing this kind of science. And I hope you've appreciated, even from the beginning of tonight, that Mars is going to be some feature. We have even more Mars news for you today. And that is because, of course, China, their Zhurong rover successfully landed on Mars only just this week. So this was May 14th, so less than a week ago. And so China's National Space Administration, I really want to congratulate them for successfully landing its Zhurong rover. It landed in the Utopia Planitia area, which I guess was last visited by the Viking 2 craft in the 70s, I think, from NASA. And I want to note that, like, Mars is hard to get to. Many countries have struggled to successfully land and keep in touch with their lander missions to Mars. Actually, China is only the second country to do so. And the future is that this rover is going to plan to study the topology and geology of that local area. It's going to examine soil for ice. It's going to survey the different elements and minerals and rocks, and it's going to take samples of the atmosphere to understand that kind of area. Now, space news isn't always backwards looking, it's also forward looking. And so next in upcoming news, and I know we're kind of staying a little bit close to home in all of these news stories, but this is just a fantastic opportunity that many of us are going to have in North America, particularly in Canada. And that is there's a partial solar eclipse happening on June 10th, 2021. It will be starting at or just before sunrise. In fact, for us in Kingston, it will start shortly before sunrise, and we will get maximum shortly after sunrise. It's going to be a partial eclipse. You have to take precautions to be able to see it safely. There's no way to view this with the naked eye safely. So we recommend checking out resources like this, which I'll put in the comments in a moment, to get more information. And at the end of this is really just a warm-up. In 3 short years, we're going to have a total eclipse here in Kingston. And so we're going to be working with local schools and local communities to make sure everybody is set up to be able to fully enjoy that total solar eclipse in 2024. So stay tuned for that. But for now, let's enjoy June 10th together. You might have to get up early, but it's worth it. It's so worth it. Okay, so that concludes space news. And so I do want to pivot now to welcome our first speaker and introduce him. And so our first speaker is Pietro Giampa. Pietro, by all means, please share your camera. Pietro, you did your undergrad and your master's at the Royal Holloway University of London before coming to Queen's for your PhD. And while you're here, you're working on dark matter direct detection using the DEEP detector. Pietro, you're born in Italy and you spent most of your life between the UK and Canada. You're a physicist by day and a basketball fanatic by night. Go Cavs, I've been paid to say. And currently you are a research scientist at SNOLAB. And you're going to tell us a little bit about how dark matter, I guess, is peppered around the universe. And I'm really looking forward to hear from you. And so by all means, feel free to share your screen and educate us.
Thank you very much for the introduction, Mark, and for the opportunity. I hope everybody can see my screen. So today I'm going to talk a little bit about how dark matter is peppered across galaxies, now how we got there. So my talk really focuses on answering 3 questions. I want to answer the question of how dark matter was created and distributed in our universe. And then I want to answer, can we observe dark matter across galaxies, so that, the answer in the first question makes sense. And then try to understand what is the impact of all of this? What does this all mean for us, especially in our universe? So let's dig in right away. How is dark matter created and distributed in our universe? Well, first off, let me set the stage for this, because we're talking about a fundamental component of the universe, dark matter, that we expect to be particle in nature. And what I mean by particle in nature is, if you look at this plot that I have here on this slide, you have a different series of sizes ranging from the microscopic scale of the size of a cat going all the way down to the subatomic range of elementary particles passing through atom, nucleus, and protons, something that we've been spending hundreds of years really studying and understanding really well. However, we expect dark matter to have really the biggest impact at the galactic scale, so at the galaxies formation and galaxy clusters and all this some scale. So I want you to understand that while we're talking about something that is spread across the universe and plays an absolute fundamental role in the structure of the universe, we are still talking about something that is particle in nature. So we're ranging over maybe 50 to 60 order of magnitudes. And if you're not familiar with the terminology of order of magnitude, a single order of magnitude would be almost like going from a basketball to a LeBron James, so from 20 centimeters to about 2 meters. The next step, order of magnitude, will be 20 meters, then 200 meters, and so on. So you can see how 50 and 60 order of magnitudes it's really a gigantic gap to go through. So how is dark matter created and distributed across the universe? Well, I'm going to be using this terminology here called DM and SM to differentiate the difference between dark matter particle and what we call standard matter particle or standard model particles. So you can think of it, if you look at this graphical representation on the left-hand side, this is a time evolution of our universe. At the very beginning, we have the Big Bang, and then as we move along time, the universe starts expanding and keep going. So at the very beginning of time, so you have to go really back, dark matter particle and regular matter particles are all in equilibrium. It's a big plasma, and there's enough energy in this very tiny portion after the Big Bang to create new dark matter, create new particle, and so on and so on. So there is this generation and formation that spawned off from the origin of the universe, from the Big Bang. Then as the universe starts expanding, so as this force that pushes the universe far apart, galaxies starts to form, starts to form, and as they start moving along, as they start pulling away, the energy content of the universe, you can almost think of it as the overall temperature of the universe, gets really colder and colder and colder as matter becomes more distant. When that happens, we eventually get to a point where there's not enough energy and there's not enough temperature in our universe to generate new dark matter. So you kind of freeze. This is the process that we call freeze out. You kind of freeze the content of dark matter in the universe, and you're left with this relic abundancy that we can see today in the fabric of the universe, for instance, by studying the so-called cosmic microwave background, which is a remnant radiation from the original Big Bang. So this is kind of how we ended up with as much dark matter as we have in our current universe. And then as the universe started expanding and moving forward, going further and further, galaxies started forming and moving around. And some galaxy, as they were moving, took some chunks of dark matter with them. Some other galaxy took no dark matter with them at all. You can kind of think of it almost as if you're an Italian restaurant, tons of people order pasta at the same time, and there's just one waiter going around with pepper, and everybody has their own preference. Some people like lots of pepper on pasta, some people don't like any pepper at all. And here's kind of a similar situation. As the universe started expanding, some portion of matter took some dark matter with it, and some didn't take any, some took little. And that's kind of how we ended up in the current status of the universe, where we see dark matter content in galaxy being different. So I pasted a picture to you, I presented a picture to you about dark matter was formed and how it goes distributed. Now, the natural question that would follow up is, can you actually see this? Can you have experimental evidence that tells you this is true? And the answer is that we do. We can observe the distribution of dark matter across galaxies. There are different ways that scientists do this. The way that I've chosen to demonstrate this for you is by looking at the galactic, what we call galactic rotation curve. So this was originally done by Vera Rubin in the 70s. She's an absolute great pioneer in astrophysics. She started studying spiral galaxies. So, and what she was doing was looking at the velocities, which is represented on this axis, on the y-axis, as a function of distance from the center of the galaxy. So you can kind of look at each and individual stars in this little galaxy and try to map out the velocity and plot it as a function of distance with respect to the center. Now, if you just have Newtonian physics or what we call standard physics or gravitational physics, you would expect a distribution to follow this dashed line, this white dashed line. However, what she observed was quite interesting. She noticed that as you go further and further away from the center of the galaxy, the velocity distribution of star didn't turn over, but it actually plateaued or even continued to rise. And so one possible explanation for this was that you actually have a halo of matter that you cannot see because it doesn't interact with light, hence we call it dark matter, that is spread across this galaxy in the shape shown by this red curve over here. And so that kind of yields you the final distribution observed by Vera Rubin. And so this is kind of how we can quantify and observe what is the distribution and density of dark matter across galaxies. And this was done, Vera Rubin studied this with the Andromeda galaxy, but people since then have looked at a multiplicity of spiral galaxies. And so here on the right-hand side, you'll see rotation curves for different galaxies of different sizes. I don't want to go into the details of what each of this plot means, but what you can think of it as if each of this corresponds to a galaxy, you can appreciate by looking at the dashed and dotted line that we explained in the previous slide. You can clearly see already that the content of dark matter in each galaxy is very different. And that kind of what gives us the idea that as dark matter froze, and we kind of ended up in this flat content of dark matter in the universe. And as the universe started expanding, some galaxy took some dark matter and some galaxy didn't. But more importantly than observing galaxies with dark matter in it, we also have observed galaxies that actually have no dark matter content at all in them. And that's actually quite exciting for somebody like me, for instance, because this is quite a strong evidence that dark matter has to be particle in nature, as I presented at the beginning of the talk. Because if you were to think of the effect of dark matter, what we just seen in previous slides, as a potential misinterpretation of gravity or perhaps some other laws that we don't know yet, you would expect that to be consistent and uniform across the universe and equal across the universe. The fact that we do observe galaxies lacking dark matter seems to reinforce our theory that is a particle in nature, and then it got distributed across the universe somewhat randomly as the galaxy started expanding across the universe. I also feel kind of sad and thinking that kind of relating to what I do, I design experiments to directly measure dark matter here on Earth, precisely 2 kilometers underground in Sudbury. And so it makes me feel a little sad to think that maybe there's another scientist like me in that universe that just can't do what I do because there's no dark matter there. And so they're in a tough luck situation. So we kind of looked at what dark matter is, what is the scale, and kind of how it was created and propagated through the universe. We showed that we can observe the presence of dark matter across the universe in a multiplicity of galaxies, and even show that we don't have dark matter in some galaxy. But what is the impact of dark matter in our universe? Because it turns out that it's not just the fact that some galaxy took some dark matter with them as they move along, but dark matter itself played an absolute fundamental role in the galaxy structure and formation. So here you can see some sky maps of galaxy structures in our universe. These are done with some telescope. You can find a reference here if you want to read more details about how this observation was made. And what you really end up seeing if you're trying to look at galaxy structure is that you have this almost neuron-like formation that you can see in these two plots. That looks almost like neurons in a brain, really, all of those galaxies and star presence in the universe, the way they formed. And so to understand whether we can reproduce this and truly understand this, what we do is that we take some supercomputers and we run this crazy box simulation in which we basically re-simulate the beginning and birth of the universe and the formation of galaxy. And it turns out, here's an example of a supercomputer simulation with a reference from a Nature paper if people are more interested in more details. And it turns out that the only real way to get to this formation, to this kind of neuron-like structure that we see imprinted in our universe, is by implementing a dark matter component in your supercomputer simulations. So without a presence of dark matter at the level of relic abundancy that we see today, meaning at the level that we expect it to be from looking at the footprint of the cosmic microwave background, you simply cannot reproduce the structure of the universe that we observe. So we think that not only dark matter was created and played a role as galaxy started moving around, but it plays an absolute crucial role in galaxy structure and formation. Which is absolutely crazy to think that there is such a huge component of the universe that we know so little about, aside from the fact that it's got to be subatomical in nature, and yet it plays an absolute fundamental structure and role for we are here and the way our universe is today. And with that, I want to thank you again for the opportunity, and I'm happy to take any questions.
Yay, cool. Thanks so much, Pietro. It was so interesting to hear about all the different ways that, I never really thought about like how important that freeze out process was, and then setting on the stage of the universe, really, of like where the dark matter is going to be found. So I encourage everybody back at home to feel free to write any questions that you have for Pietro. I do have a couple that have come in already. So Sean asks, just a clarity, I think you mentioned about the particle in nature, like the particle nature of dark matter. And so he was wondering if it's a particle, would it have like an antiparticle as well? Like could dark matter be antimatter as well?
Absolutely. So at the moment, we're using the dark matter term as a very generic sort of catch everything terminology for this, 30% almost matter content of the universe, energy content of the universe. But the reality is that it doesn't have to be a single particle or a single instance of subatomical nature. Dark matter could be a very complex structure of subatomical particles. If we look at, for instance, everything that we've been able to understand and study about what we call regular matter, which only makes up for about 4% of the total energy content of the universe, and think about the complexity that the standard model, as we call it, poses, it's not unthinkable to think that dark matter may be at the similar structure, and so it's not unthinkable to think that there is a particle and an antiparticle that composes dark matter.
So cool. Another question is like how abundant should we think of dark matter? Do we think it's like literally everywhere, that it's even here? Is it on the Earth, throughout the Earth? Is it in this beer glass?
Yeah.
Or is it only present on like galactic scales?
So we have observation and study from our own Milky Way, so we know that there should be a presence of dark matter in our galaxy, at least from what we can gather from measurements. And based on what the estimate density of local, as we call it, local density of dark matter in our universe, there are dark matter particles flying around us all the time. They're just very antisocial. They just don't like to communicate with regular matter that often. Just to give you an idea, even if you take a best case scenario in which a dark matter particle just lies an inch away from what we've been able to look for with our current detectors and our state-of-the-art science, you still be looking at maybe 1 or 2 interactions of dark matter particle with your own body per year. So it's a very, very antisocial, let's say, subatomical particle. But we are surrounded by it, and it's just flying through us like a ghost every single second.
So dark matter does not want to get COVID from regular standard matter. Another question from Sean, it's kind of 2 parts. He's saying that hopefully someday soon we can directly observe, detect, and record dark matter. And so kind of a follow-up question I asked is, when do you think we're likely to actually find it? And then kind of tied into the antisocial nature is, do you think once we kind of perfect an ability to detect it, could we actually make technology to maybe contain it or like hold it in some way?
Yeah, that is a great question. To answer the first part, the sooner the better, really. But when you do these kind of searches, you never know, right? So it's the way I can explain it is that it's kind of looking for your keys in a castle when it's really dark. And so the only thing you can do is slowly go room by room and eliminate every possible room until you find your keys. And the reality is that your keys could be at the next room you look for, or they could be about 1,000 rooms away from you. But the only thing you can do is do your due diligence and keep going room by room and check, cross all the T's and put dots on every I's until you find and understand more what it is. To the second part of your question, which is super fascinating, I would say, I think that to play it a little bit more on the sci-fi side of things, the possibilities are somewhat endless, really. It's difficult to imagine what you can do when you discover new components and new fundamental blocks of the universe. I'm sure that whoever discovered the transistor back in the days didn't imagine, the technology that spawned off from this, or whoever discovers, superconductor didn't imagine quantum computing being a reality. So it's difficult to say where we can go with it. First step is try to understand what it is and kind of how it communicates and works in the surrounding, and then we'll see where it goes from there.
Alrighty, I think that is all the questions we have at this moment. Pietro, you're going to maybe be able to come back and answer a couple more questions if any more come in at the end. We'll have all the speakers together in case there's any more questions. But for now, I really want to thank you very much for your time this evening, and thanks for a great talk.
Thank you, guys.
Cool. So at this point, I would like to turn to trivia, space trivia, and let's see if I can get my presentations going again. So, cool, sorry. You get to just look at me. Zoom is hiding itself from me. Here we go. Yeah. So if you, in the description of YouTube, let's go back. In the description of YouTube, you should see at the very top, there's a link to a form that you can fill in. If you, in that space is a place where you can answer these, we're going to have 2 rounds of trivia, 5 questions each. You can fill that in and fill in a bit of your contact information, where we can then get in contact with you if you're one of the winners tonight. And we will see if we can go through all the answers tonight and actually be able to announce live who the winner is. But to begin, let's start off round 1 of trivia. And well then. So I have a helper in the background, Nick, and he does have the link to the form itself, but let me just get it up here. Because this is clearly key. You need to have it as I do the trivia itself. So we will go to, I'm gonna, Yep. So I don't know. Right, so I've been told that none of the form is working for you. And if I have to guess, it's because I originally copied the settings. That's exactly what happened from the last time we did this, which then had a window for when they're allowed to access it. So I can go accept with no start date, no end date. You guys, if you refresh, you might have to refresh the page. You should be able to access it now. And maybe, is it working now? And I can, works now, yay. Sorry about that. I had a window. If you, I don't understand why none of you don't have a time machine. You could go back to January and do it then. Unfortunately, one of our trivia questions is not how do you invent a time machine? So we'll have to find that out another way. But for now, my understanding is you guys all see the form, and so we can begin trivia. And the first question is, what sort of electricity do you get when you rub two balloons and they stick together? Which planet, these are on a timer. I'm just gonna go, and I'm gonna repeat all of these questions. Question number 2 is, which planet has the largest ocean? Question number 3 is, when the Mars rover Perseverance landed on Mars, how long was the delay before we knew it landed successfully? And I will do a repeat because I know number 2 went by really quickly. So question number 3, when the Mars rover Perseverance landed on Mars, just how long was the delay before we even knew it had landed? And keeping in mind the distance to Mars and the fact that light takes time to travel. All right, question number 4. Name this object. What is that thing on the screen? I don't know why it keeps doing that. And question number 5 is, name the movie that takes place almost entirely in the lunar base and stars only one on-screen actor. So not including any voices you might hear with famous actors, I just on screen, who is the only actor that you see. Okay, and I'll go through these just one more time. So question number 1 was, what sort of electricity do you get when you rub two balloons and they stick together? Question number 2 is, which planet has the largest ocean? And to narrow this down, we are only accepting planets in our own solar system. Which planet has the largest ocean? Question number 3, when the Mars rover Perseverance landed on Mars, how long was the delay before we actually knew it landed successfully? How long? Was it an hour? Was it 10 seconds? How long? Question number 4 is, how or what is the name of this object? So this is a large machine, it appears, of some sort. What is the name of it? And last but not least, question number 5 for round 1. And so when you fill this in, you can just leave that form ready, and then you'll come back to the form for round 2. But round number 1, please name the movie that takes place almost entirely in a lunar base and stars only one on-screen actor. What is the name of that movie? All right, that concludes round 1 trivia for tonight's Astronomy on Tap. So with that, I want to take the opportunity to introduce our next speaker. And so I would like to welcome on Akanksha Bij. So Akanksha is a first-year master's student at Queen's University in the astronomy department. She's currently researching the role of magnetic fields in star-forming filaments under the supervision of Professor Laura Fissel, another Astronomy on Tap alum of Kingston. Akanksha did her undergraduate studies at the University of Toronto in electrical engineering. A fun fact she wanted to share with you tonight is that one thing on Akanksha's bucket list is to publish a novel, but she admits that she is currently nowhere as close to that. And so I really want to apologize to you, Akanksha, for taking you away from your life's goals, but I really want to thank you for sharing your time, obviously your really high value time, and sharing that with us this evening. So I really look forward to your talk. You have a very interesting title, and I don't know if it's going to make me happy or sad. So tell me, it started with a bang, but how is it all going to end? So I look forward to hearing from you.
Great, thank you for the introduction. And don't worry, this is also one of my other life goals, so you're not taking me away from anything. Yeah, so as Mark mentioned, my research is within star formation, but today I'm going to be talking about something slightly outside of that. So we'll be talking about the ultimate fate of the universe. So we know that it started with the Big Bang, but the question is, how will it end? And will it even have a definitive end? And how will the universe look into the deep future? So this question has long been asked by poets and philosophers alike of will it end in fire or ice? An example of this is the poem by Robert Frost, which goes, some say the world will end in fire, some say in ice. For what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to know that for destruction, ice is also great and would suffice. So this is the question that we are going to try and answer throughout this talk. So if you have a hunch, or maybe you've seen this before and you already know, leave some comments in the comments section, and we'll return to this at the end of the talk and see if you were right. So whether the fire or ice scenario plays out, this really depends on the ongoing tug of war between gravity and dark energy. So to begin with gravity, we know that any matter that has mass is going to have a gravitational field and is going to attract everything else to it. And the more massive that object is, the stronger this force of attraction will be. But the further away that you go from that object, that's when the force of gravity weakens, because it depends on distance. And so when we're talking about the scales as large as the whole universe, gravity is going to be acting on much smaller, more local scales, like our solar system or within a galaxy or a cluster of galaxies if they are close enough together. On much larger scales, though, we know that the universe is expanding, and it's thought to be expanding by a mysterious energy that we call dark energy. How this dark energy works and how it changes over time is something that is not really well understood right now and is still at the forefront of research. What we do know is that the universe its expansion seems to be accelerating. So it's expanding faster and faster. And so on the one hand, we have gravity trying to pull everything together. And on the other hand, we have dark energy, which is trying to pull everything apart. And which of these two will win at the end depends on the shape of the universe, the amount of dark energy, and how this dark energy is going to change with time. So as I mentioned, the second and third point is not that well understood, but we do have a pretty good idea of what the shape of the universe might be. So there are three possible geometries that the universe can take on. Here for simplicity, it's shown in 2 dimensions, but you kind of want to think about this concept extended to 3 dimensions. So in the first case, if there was no curvature or we had a flat universe, this would be the case where all of our usual rules of geometry still apply. So parallel lines will forever stay parallel. The Pythagorean theorem would still apply. And if you were to sum up the interior angles of a triangle, it would still add up to 180 degrees. However, if the universe had some curvature to it, then our usual rules of geometry no longer apply. So if the universe has a positive curvature in the second case, which is a closed system, then parallel lines would eventually meet. And if you were to sum up the interior angles in a triangle, it would actually be greater than 180. The inverse of this would be if there was negative curvature to the universe, then our parallel lines would eventually diverge. And if you were to sum up the interior angles, it would be less than 180. So the consensus right now is that our universe is almost pretty much flat. And this will have some implications into its ultimate demise, which we will see. So we know that it's a flat universe, but depending on how dark energy is going to change over time, this can result in some different scenarios for how the universe will eventually end. So the lines that are drawn here are showing you the expansion rate of the universe. So we see from Big Bang to today, the expansion has accelerated. But in our first scenario, we could have the acceleration go to a maximum point and then start compression. And this scenario is called the Big Crunch. In orange, we're showing a second scenario where the expansion could accelerate so fast, and this would result in a second scenario that we'll call the Big Rip. And in the third case, the expansion will continue as it's been going, and this will be called the Big Freeze. So we'll talk about what each of these 3 scenarios will look like in turn. So starting with the Big Crunch, this is the scenario where the tug of war, gravity will win. And it would essentially look like the opposite of the Big Bang. So in the Big Bang, we started at a single point and expanded. So this will be after reaching a point of maximum expansion, we're going to compress back into a singular point. So this would be our fire scenario. And that is going to be ending in an explosion. So this would be most easily achieved if the shape of the universe was closed. And but it can also be possible for a flat and open universe if the rate of expansion, what we call the cosmological constant, was negative. So this is the first scenario, the Big Crunch. In the second, and so it's thought that, well, maybe there was already a crunch before the Big Bang. And this is another hypothesis proposed, is to thought that, well, maybe the universe cycles between expansion and contraction. And so we go through cycles of Big Bang, then Big Crunch, and then back to the Big Bang, each time creating a new universe. So this is known as the Big Bounce theory. And while it's pretty interesting, it's thought not to be very likely. The second scenario that I mentioned earlier, instead of gravity winning, this time dark energy would win, but it would almost accelerate to the point of infinity, and would actually not only overwhelm gravity, but also overwhelm the nuclear forces that are holding atoms and matter together. And so this is aptly named the Big Rip, because it would tear apart the fundamental matter, and expansion would just overwhelm. That is a pretty dystopian future, but don't worry, there's also another scenario. Oops, misplaced twice. Okay, so this is most easily achieved for an open universe, where even if there was no dark energy, it would accelerate, but it's also possible for a flat and closed universe, depending on how much dark energy there is. Okay. So for our third scenario, if dark energy would win, but not to the point of infinite acceleration, if it just continued expanding without actually overwhelming the nuclear forces, we could have expansion continue and without tearing apart matter. And this is known as the Big Freeze scenario. And if you can gather from the name, this would be our scenario of the ice. And so this is most easily achieved for open and flat universes, but can also be in the closed universe, again, depending on how much dark energy there is. Okay, so let's now take a journey through deep time and look at what this freezing would actually look like and what our universe will look like in the future. So we can split our future universe into different eras depending on what stellar objects or what astrophysical objects are dominating the night sky. So currently we live in the age of stars, and stars dominate our night sky. So this era is known as the Stelliferous era, but that won't always be the case. So stars are being generated within, are being formed within galaxies in their stellar nebula, but that rate of formation of forming new stars is declining, and we think it's eventually going to peter out and stop completely. So no more new stars will eventually be formed. And all the stars that do exist are going to die. So let's take a look at the different ways that stars can die. So for the low and medium-sized stars like our sun, they eventually turn into what's known as a white dwarf. And for the massive stars go supernova and eventually turn into either neutron stars or black holes. So the fate of a star depends on its mass, but its lifetime also depends on its mass. This time, the smaller stars are actually going to live longer, and the smaller stars, the longer it lives. So the smallest stars are red dwarfs, and they live for a really long time. In fact, all the red dwarfs today have only gone through only 1% of their life. So they still have 99% of their life to go. And it's going to take them a really, really, really long time to die. In fact, it's going to take them 10 to the 13 years for that last red dwarf to die, an insanely long amount of time. So you don't have to worry, this isn't going to happen anytime soon. So I hope I'm not going to make Mark cry. Okay, so all that will be left once that last red dwarf dies is going to be white dwarfs, neutron stars, and black holes. And these will be alive for a long time, but remember, we're going so far deep into the future that we're going to let that time pass. So eventually our white dwarfs and neutron stars are also going to die. So white dwarfs can either cool just over time, the way cinders cool, into what's known as black dwarfs. And again, this takes a really long time that there's actually no black dwarfs in the universe right now. We can also have white dwarfs accrete matter or collide into each other and go supernova, turning either into a neutron star or black hole. Same with neutron stars, they can collide into each other and turn into a black hole, or they can also have their own death. This is, again, a little bit mysterious and not that well understood because the physics of neutron stars is quite exotic, as there's a lot of quantum effects that come into play. But we think that eventually there might be some disintegration of their matter in a supernova-like way. And so neutron stars will also eventually die. And so this is known as the degenerate era. It's going to be a graveyard of just stellar corpses. And we think that in the end of the degenerate era, by 10 to the 40 years, which is a crazy long amount of time, the last survivors will just be black holes. One thing to remember is that as the universe is expanding, it's going to be a lot harder for light that's far away from us to reach us. And so what's known as the observable universe or the cosmic horizon is going to be steadily shrinking. And so if any intelligent life is still around at that time, it's going to see even less and less of the universe. So if from our Milky Way, if we are still around then, if we were to look out around the degenerate era, the only thing that we will be able to see is what will be our Milky Way. And by that time, our Milky Way will have merged with other galaxies in our local group. And so we'll just be able to see only this one elliptical galaxy and nothing else really. So after the white dwarfs and neutron stars are gone, the only thing left is going to be the black holes. And so this is when black holes will dominate the universe, and this is known as the black hole era. This is quite creepy to look at, but here we go. So we have just black holes that are orbiting one maybe more massive central black hole. And this is going to happen very, very deep into the future. Again, this is just an unfathomably long amount of time. So typically we're used to thinking of light that goes into a black hole, it stays there forever. But remember, on these time scales, the word forever really has lost all meaning. And so it's black holes eventually do also die, and they die by evaporating in a phenomenon that's known as Hawking radiation. And so they eventually end up losing their light and mass. And this happens very, very weakly and very slowly and takes a long amount of time. And the more massive black holes evaporate more slowly. And so the most massive black holes that are in the center of galaxies, our supermassive black holes, are going to take the longest to evaporate. And so by the 10 to the 92 years, that is going to be when really the last black hole is around that time is going to evaporate. And so that's it. So that was our last surviving grand structure in the universe. And so the question is, what happens next? Oops. What happens next? Well, it turns out that nothing happens next. So after the last black hole has died, there's going to be no large scale structure anymore. The only things that will really survive are some photons and subatomic particles. And this will pretty much go on till infinite time, if time even really has any meaning at this point. And the universe will just be very cold. And because now everything will come to the same temperature, and you usually need a difference in heat for things to happen. At this point, there will be no differences in heat, and that will be known as the heat death. Okay, so to return to our question of will it end in fire or ice, based on our current understanding, it's thought that the universe will in fact end in ice. So this is the way the world ends, not with a bang, but with a whimper. And that's from T.S. Eliot. So this was slightly bleak, but I also think it's quite beautiful. And I hope I didn't give anyone an existential crisis so early on in the evening. But if you have any questions, I can take them now.
Thank you so much, Akanksha. Yeah, I didn't shed any tears. I guess it's long, long in the future, but it does get me thinking about, yeah, just what do we do then? What do people do? And it reminds me of a story. I don't know if you've read it, called The Last Question by Isaac Asimov, which is about exactly this. It's about the heat death of the universe. So yes, thank you again for a great talk, even if it's, I don't know, from the universe's perspective, maybe a bit depressing. Maybe I'll stick with the cyclical big bounces. That's encouraging. At least it's universal cycles. So yeah, so if anybody has questions for Akanksha, then please do share them. One question that was brought up is like, what actually sets the shape of the universe? And maybe you said this, but why is it possible to be flat or curved or closed or open? Like, what sets that?
Yeah, so that's a great question. Oops, did I stop sharing? I can start sharing again. Yeah, so that's a great question. It's actually set by density. So there is a critical density, and if the average density of the universe is just around that critical density, that's how you get the flatness. And then I'm not a cosmologist, so I hope I don't say this backwards. If you are maybe above the critical density, then either that will give you the closed or open case, but because in our actual universe, it's just about that critical density, which is kind of amazing. And that's what's giving that flat shape.
There's just the right amount to keep it perfectly flat. So cool. Okay, so one question, and I get this whenever I'm at a cosmology talk, I see this question. And so you're on point.
I think I know what it is.
And it is, if the universe is expanding, what is it expanding into? What's outside the universe? Is it unlimited? Yeah, just what's this idea of like, what's it expanding into?
Yeah, I anticipated this question too. Yeah, so universe is everything. So we don't want to, it's not expanding into anything really. What is a better way to maybe think about it is the fabric of space and the things between it. That's what is stretching. And so it's just the space is increasing, but it's not really expanding into anything. It's a little hard to wrap your mind around at first. You kind of just have to accept it. But yeah, I think the visual of like a balloon or something expanding can be kind of misleading. Yeah, so it's just the 3 dimensions that's already just kind of the space between everything is what's expanding.
Yeah, it's always a little bit of a hard one to wrestle with. I had a question, which was just like, how long, you said there's no, what do they call them, dark dwarfs yet, but they sound like such a cool thing astrophysically. So like, just how long does it take to go from a white dwarf to a black dwarf?
Yeah, I don't know the number off the top of my head, but it is, so right now we're at almost 14 billion years and we still don't have one. So it's definitely longer than that. And yeah, they cool extremely slowly. Yeah, so it takes a really, really long time to go from that white dwarf to a black dwarf. But it could also be that because it's black, it's hard to see. So maybe we just haven't seen one, but we do predict that it does take very, very long.
Cool. Well, something to look forward to maybe.
Yeah.
Another question was, yeah, is there a theory? I think this goes to the Big Rip idea, is like, at what point is it possible that this actually rips apart matter? It seems like in the freeze out, you don't get that. You don't have that infinite expansion, but like, what is it that allows maybe really, really big expansion to actually rip apart matter, whereas other models don't? Like, like it just seems crazy that there's a force that could literally rip apart matter.
Yeah, so the visual I showed with the shrinking observable universe, eventually you could shrink so that particles can't even talk to each other because even they need to interact. So it's going to shrink. So we couldn't see beyond our own galaxy, but it can shrink so far beyond that, like the proton can't talk to its electron anymore. And that's what's going to kind of create that Earth. And the force is not going to be able to reach anything beyond its own little shrunken cosmic horizon.
Wow, it's like the cosmic horizon would be smaller than the interaction between even the quarks and atoms and stuff. That's crazy to think about, but yeah, that's crazy. Okay, that is the last of the questions for now. Again, Akanksha will be joining us at the end as a bit of a panel if there's any more questions that come up. But for now, I really, really want to thank you, Akanksha, for that great talk.
Great, thank you.
And let me share my screen. I'm so happy that the trivia forum did work out once I made that little switch. Sorry about that. And so with that, we are ready now for the auto advancing trivia of round 2. And so we'll begin with question 6 with a simple name that scientist. He almost should be identifiable more by the pipe than the telescope in front of him. So who is this scientist? All right, and question number 7. We saw that there was a lot of excitement about the movie referenced in round 1, about the interesting plot without necessarily spoiling the movie. We're going to ask you another movie question, which, as I understand it, is not as good as the movie in round 1. It's different. So name the movie where George Clooney plays an astronaut stuck on Earth trying to save returning astronauts who don't know what awaits them when they arrive. That's a mouthful. So name the movie where George Clooney plays an astronaut stuck on Earth trying to save returning astronauts who don't know what awaits them when they arrive. What's the name of that movie? Alrighty, going back to Mars. So recently, Mars has been an active spot for space research. Name the only 2 countries to successfully land a rover on Mars. Recently, Mars has been an active spot for space research. Name the only 2 countries to successfully land a rover on Mars. Alrighty, question number 9. What rock floats in water? And in my head, I'm hearing Hank from Breaking Bad saying it's minerals. What mineral floats in water? But we'll say, what rock floats in water? And question number 10, I'm going to repeat all of these, is which planet has the shortest day-night cycle? Which planet, in essence, is spinning the fastest so that a day-night goes by the quickest? Which planet is it? So let's do it one more time. Trivia round 2. Please name the scientist for question number 6. What is the name of this person? Telescope wielding, pipe wielding scientist. Question number 7. Name the movie where George Clooney plays an astronaut stuck on Earth trying to save returning astronauts who don't know what awaits them when they arrive. Bum, 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 George Clooney. Without his useful sidekick, Brad Pitt. It was a different sci-fi movie. All right, question 8. Recently, Mars has been an active spot for space research and space news, as we saw. So name the only 2 countries to successfully land a rover on Mars. Question number 9. What rock floats in water? What rock just happily just floats? It has to be a rock. It's not these like weird aerogels or whatnot that are created in the lab. We want an actual natural forming rock. And question number 10, which planet has the shortest day-night cycle? So you have until about So I'm seeing it's 8:04. I'm going to give you just until the next speaker starts to submit your answers. Make sure you submit the form. And then my good accomplice, Nick Aurora, will get to work trying to see who has the right answers. And so with that, I would love to turn to our last, but not least, speaker of the evening. And so let me do a proper introduction. So our last speaker tonight is James Fraser. James is a professor in the Department of Physics, Engineering Physics, and Astronomy at Queen's University. And James leads an enthusiastic research team exploring laser applications ranging from fundamental studies of nanomaterials to solving industrial problems. His laboratory is rather unique, containing lasers capable of outputting femtosecond duration pulses to kilowatt-class industrial fiber lasers, such as used in automotive and aerospace manufacturing. James would also like to claim that the fact that his last name rhymes with his area of research was just lucky. And I have to admit, James, I'm not going to believe you until I have a chance to talk to your parents. But in the meantime, I do think that we are lucky to get to hear from you tonight. So I really look forward to hearing from you about how lasers help us understand the universe, and take it away.
Thanks so much, Mark. I think I am the least in terms of last and least, and I'm okay with that. Those were some great talks. But I have to say the vision that I'm stuck with is from Pietro, of the fact that that scientist in the galaxy with no dark matter working so hard in his lab building a dark matter detector, not knowing that it just isn't going to work. That's just so sad. All right. So Mark, of course, talked about this event as being a discussion. Been lots of great discussion in the YouTube live chat. In these sorts of events, sometimes I feel a little shy putting in answers and those sorts of things. And so maybe some of you are the same way. So I just wanted to use this poll everywhere software, because I'm going to throw some questions at you. There's no grading involved, and my questions don't involve any prizes. The way you can access this is either just grab your smartphone, turn on the camera app, and direct the phone at that funky looking code on the left-hand side. Give it a moment and it'll come up with the link, or you could just open up a browser and directly type in the link. And if Mark can throw that text into the YouTube chat, that might make it a little bit easier for you. What you're going to see then in there, you don't have to log in. There's no collecting any of your information. I'll just give you a question. I'm going to do this a few times through. So if you're able to do this, please do. If not, that's okay. And already I'm seeing a bunch of answers coming in. So thank you for that. So while you're doing that, let me just sort of give you a bit of a preamble to, why am I here with you? Even though the experiments that I do are not these, beautiful things that we've been talking about in terms of understanding the cosmos. Maybe something that you'd see in my lab would be using a laser cutter to try and process some advanced alloy in a new way. You might think that this looks completely different from the sorts of applications that and areas that we've been talking about in the earlier talks. But in fact, there's some things that are very, very similar. One way to think about this is, why do these different fields use laser beams? Why do we make use of this tool? And I just want to highlight how different a laser is from a regular light source. You can think about the spotlight. The light is it's a mess. It's going in all directions. It's not very uniform. And even a cheap laser pointer gives you immediately see what's so valuable about it. All that energy is all flowing in almost exactly the same direction. And that's just going to keep going on for forever if we don't block it or absorb it. So that's what we use in astronomy type applications, which I'm talking about today, or in terms of my lab, focusing it down to very tight spots. We can do that because it's so well controlled. All right, so just to give you a sense of where you guys are at in terms of your responses, a third of you did say when you hear lasers, you start thinking Star Wars or Dr. Evil. Certainly my in-laws love to tease me about that. They keep asking me if I built my laser yet or not. The problem, though, I want to talk about it here today is not world domination. The problem is a very important one in observational astronomy, and that is most of our instruments, most of our telescopes are on the Earth, and we got to look through that big murky atmosphere to be able to see these distant objects. Question I want to ask you then is, have you seen, with your bare eyes, have you experienced distortion due to air movement? So just the fact that air is moving, does that mess up? Does that give you fake images? In terms of astronomy, what am I talking about? We might have some distant object that truly is this, but once that light goes through the upper atmosphere, bounces off, refracts due to different density of gases, it ends up looking like this, just a big blob. The big challenge is, how do we, oh, sorry, I didn't activate my poll. I got to activate it. There we go. So that question now is on that other browser. You can say if you've seen any evidence with your own bare eyes of this effect that plagued astronomers for so long, this fact that the air bends the light because the air is different densities at different places, different temperatures. Let's see, let's give you some hints though. Maybe you've seen the sun at sunset. Of course, the sun is a pretty good circle, but here we see it distorted. And then of course, an example of the distortions that you might have seen with your bare eyes, stars twinkling. So that twinkling is giving you a sense of the light that's coming through the upper atmosphere getting distorted. It's beautiful when you're out on a late night looking at the heavens, but for astronomers, this is a real problem because it blurs our images, blurs their images. All right. The good news is we have a way of correcting it, and that's known as adaptive optics. The air, just to give you a sense of a cartoon of how this happens, the air might be distorting the light. It makes the light waves all messed up, but we send it against a deformable mirror. This is a mirror that the shape is actually can be very complicated and can be controlled. Hundreds of little actuators moving the mirror back and forth to change the shape to exactly cancel the distortion to get a nice, clean image. Well, there's two pretty big problems here. One is, if we're going to remove those distortions, we need a mirror that's going to change its shape at the right speed. And I'm going to ask, and of course, I'm assuming not many of you are designing these sorts of things in your telescope facility. I'm asking right now in that other window, your poll everywhere window, how fast do you anticipate, how fast do you think such a deformable mirror needs to change? So if you want to just go to that window and answer that question, I'll give you a little bit of time just to do that. I'll make the comment that you have your own personal experience that's already given you some data to help you understand that. Go back and think about the stars that are twinkling. They're twinkling at the speed that the air is moving. So it shows that it's not going to be good enough to change this mirror every second or every minute. You're going to have to do it hundreds of times per second. The second problem is how do you know how to change the mirror shape? That's going to be problematic if you don't know what shape to make the mirror. And the way that solution that we do, we use lasers. So it turns out there's a thin layer, 10 kilometers of sodium atoms that we can actually send a 20, 30 watt beam of yellow light that will bounce and hit those sodium atoms. It gets absorbed and then emitted. So think of it as being like a light bulb hanging in the sky exactly where we need it. That light then comes back down, gets perturbed, distorted by the atmosphere. And our instruments are able to then see that, figure out the distortion, change the deformable mirror, and doing that all hundreds of seconds so that we can go from a blurry image to a nice, crisp, precise image. All right. So this talk could then be exploring a lot of these types of images that we're able to achieve with this technology, but that's not my area of expertise. I'm really interested in how do we take an idea from one place and use it someplace else? This is a great idea. Can we use it someplace else? Let's go visit the laboratory of Melanie Campbell at the University of Waterloo. She's really interested in making use of imaging of the retina, that's the back of the eye, for identification of disease. The problem is, especially for older folks, the lens distorts the imaging. So it degrades her ability to be able to make any sort of medical assessment. Well, what did Professor Campbell do? She took ideas from astronomy using adaptive optics to be able to correct for those imperfections of the eye, to be able to see right down to the single photoreceptor. And this is believed to be very useful for even things as important as Alzheimer's diagnosis. And think about it, this is non-invasive, doesn't hurt, quick, and it's only possible due to taking these ideas from astronomy. All right. I said that I'd talk a little bit about unraveling the cosmos with lasers. I just can't not talk about this other application just because it really has opened up a whole new window into the universe. Think about two black holes. We were, earlier talking about, dissipation and evaporation. Let's just talk about merging here, where huge amounts of mass are changed into energy, and that energy ends up distorting the very space-time with those gravitational waves spilling out, traveling from galaxy to galaxy, and finally reaching us. Now, the amount of stretching and squishing that happens is incredibly small, but we're able to now see it. How do we do it? By using lasers. The way we do it is a very well-controlled laser beam, pretty good amount of energy, but split into two along two incredibly long paths. And if one path moves even 1,000th of a meter, much, much less, in fact, they're able to see that result because light, that is a wave that is being recombined from these two paths, will interfere. You can think about this intuitively just in terms of water waves, that if the light from the crest of one path lines up with the crest of the other, you're going to get a bigger wave, more intensity. Or the path might change a tiny little bit. You get destructive interference and you see no light on the detector. And this, of course, has opened up a whole new window into the universe using this gravitational waves as the way of collecting information. Well, I can't not talk about a neat idea and how this idea can also travel from work that I do in my lab and applications. We need a more sustainable future. We need lighter cars. We need cars that are able to survive longer. So it needs new materials. And new materials always bring about new challenges in manufacturing. We can use lasers to actually do things like weld these new materials together. But a basic problem is the weld deep enough? We have to measure its depth. Measure its depth. That sounds pretty familiar to what we were just talking about. And that's the approach that we actually took in my lab. We made this sort of laser yardstick device, but now we use it for measuring how deep a laser weld is. And this has been really very useful, so useful, in fact, that there was a spin-off company with many students from Queen's University in the picture, and they are now commercializing and selling these systems around the world to automotive and aerospace manufacturing facilities. Well, the last question in my poll everywhere poll, what were we talking about? What do you think is most interesting? Can't get this one wrong. You'll know best. Using lasers to create these artificial stars in the heavens so that we can correct for the blurring of the atmosphere, or using lasers to be able to detect minute changes in the stretching and compression of space-time here on Earth so that we can understand and look at things, cataclysmic things happening very, very far away, or making use of good ideas and letting them really travel to have impact in fields as different as, medicine and advanced manufacturing. Well, I'll keep that poll open so you get a chance to answer. And thank you very much for your attention.
Thanks, James. You shined a light on really interesting laser work.
I see what you did there.
So the first question has to be, how are you getting along putting laser beams on sharks?
They won't stay still. They keep swimming away. But I will make totally honest, photonics and light is such a fun field because it has impact in a wide variety of areas. Not on sharks, unfortunately. Well, there is actually a publication that did that. But there was actually, we had an effort with understanding fish vision in Lake Malawi of Africa because it turns out fish have some really interesting, those fish in particular have really interesting ability to measure light. Anyway, I digress.
I mean, that sounds really fascinating. So I guess you know what you're talking about next time.
Actually, I see on the poll, Mark, and thank you folks for doing the poll. And I apologize if I wasn't using the poll quite properly. The by far the most interesting is sensing gravitational waves. So I think McDonald Institute should definitely bring in an expert on that, because there's a lot of interest in that. And it is just beautiful, so beautiful research.
Sounds good. Sounds good. Yeah, I am really, really interested in the whole gravitational wave. We've gone from looking at the universe and hearing it in a sense, and seeing the ripples in space itself. So there was one question, I think it was Sean was talking really about, like, okay, the lasers make quite the case for trying to overcome the atmosphere, but satellites, are also very nice for getting above the atmosphere. And so my question to you is, and I know you're not an astronomer first, but if I was to give you the poll, which do you say is better, Earth-based or space-based telescopes, knowing that you have these cool laser technologies to try to overcome the Earth's atmosphere?
Yeah, so I mean, from what I see and what I read, and as you say, I don't want to represent myself as an astronomy here. My astronomy buddies will beat me up if I try and make that claim. But definitely the bottom line is you can have a bigger mirror on Earth than you'll ever be able to have on a space platform. And a bigger mirror gives you greater ability to collect light. That said, what I find really exciting stuff about space-based telescopes are to look at signatures that just can't even get through the atmosphere. So the new telescopes that will be coming online, and I'm sure, Mark, you know more about this than me. So the idea is that it's not just the problem of distortion, it's that certain parts of the electromagnetic spectrum we haven't had access to because they just get blocked. So that's where that space-based telescopes are going to be so exciting, to be able to see things that, I mean, literally we've been blind to.
There's a question from Roger, who's interested in lasers, about, is there any ability to kind of change the speed of the light, maybe accelerate them even faster than what they go in a vacuum, or maybe slow them down?
So there's really interesting literature on this. So there was this race of people creating new different types of matter that would slow the light pulse down. And they had a lot of fun with even how they did the titles of the papers. So light pulse slowed down to speed of airplane. Then the next one was light pulse slowed down to speed of VW bug. Then the next one was like light pulse slowed down to person walking, until the point where they actually were able to have a material that the light was actually able to stop. And why that ends up being really interesting, I mean, it's just can you do it? It's just an interesting question. But also now you start thinking about, you're effectively just created a storage device for that light. So that opens up new areas of potential applications. The going faster, there's some little nasty sort of, actually there's these little tricks where people have claimed faster than the speed of light, and it ends up really just taking a pulse and reshaping it, which, Frank, I don't think that's nearly what Roger's really talking about, because that's not really that interesting. It's just people, I would say, playing games with it rather than really, achieving that. So, no.
So what does stopped light mean? Like, how should I interpret light that has been stopped?
There's so much things about it that are really strange, because of course, if you have a pulse that goes into this material, even let's just say the case where it's not stopped, just slowing down, as the pulse gets to the front of the material, it'll start, the back end still keeps coming in. So the light pulse intensity goes insanely high. And now you can easily start getting into intensities that rip apart the very atoms that are involved there, just because you've physically compressed the energy into a smaller space. But in terms of stopped, what it ends up being is an interaction with matter. So a way of thinking about that is that the matter absorbs the light, puts it back out, absorbs it, puts it back out, absorbs it, puts it back out in this cycle, so that it never can really keep moving and get out.
Okay, another question is on LIGO. Something that's always been kind of interesting to me is it's an infrared light. And I'm thinking about how much precision it needs to have in the width. And my first instinct would be like, I somehow need to have a light whose wavelength is smaller than the stuff I care about. But they're using the super long laser. And I'm wondering if you could, are you able to speak to that at all about like, why is an infrared laser the way to go?
Yeah. So, of course, the technology of LIGO, I mean, I love the images that they create of merging black holes, but what really just blows me away is this technology. Because as you said, the picture that I gave between, wave crests overlapping crests and then having a shift of a crest overlapping with a trough, that's a distance on about a quarter of the wavelength being, infrared, as you said, say about a micron. So that's 200 nanometers. Well, they have to go to see these gravitational waves. They have to go orders of magnitude, even more precise. I'll say that it really comes down to that we don't need to go all the way from crest overlapping with crest to crest overlapping with trough. So now it just becomes a case of how sensitive can I make my system so even a slight shift, a very small shift in the trough of one compared to the crest of the other ends up corresponding to a very small shift in the intensity, but it still is measurable. And they're making use now of these really neat laser light sources that on purpose create, I would say, really precise where the crest and trough is. So they're pushing laser technology design. I think that's really neat, right? Even though the application is seeing gravitational waves, they're driving improvements in the technology. And, as was discussed earlier, who knows where that's going to come out to be useful. It will be, I guarantee you, and I guarantee you we could not predict where it's going to be useful today.
Cool. So there's a question from Nikhil who says, hey, Professor Fraser, what about lasers in space travel? What are your hopes and thoughts about things like breakthrough starshot and future potential applications of lasers?
So breakthrough starshot, for those of you who don't know this, is this pretty well-funded effort that is trying to send a craft to the nearest other star system. Alpha Proxima, I think. I shouldn't actually say because I'm probably going to get it wrong. Which one is it?
Proxima Centauri, which is
Proxima Centauri. Thank you.
Yeah.
Now, the way to do this, I mean, it just would take too long if we could only go, 100th the speed of light. The craft has to be accelerated to a sizable amount of the speed of light so that it could get there in our lifetime, sort of thing. And the way that they are thinking about doing this is by using a light sail technique. The idea is that if I have light that hits an object and bounces back in the exact same way, if I had a basketball that hit an object and bounced back, that you felt this, you feel a little bit pushed backwards. Well, think about that doing with a photon. The photon doesn't give it a lot of motion forward, but I can make a lot of photons. So the challenge is to create a massive laser on the Earth that would be able to target this tiny little sail up outside of our atmosphere to generate a huge amount of acceleration so that it could get to a sizable amount of the speed of light to get to that star system within 20 years. It's the technical challenges here are insane. I mean, just right off the initial problem of you're hitting something with a lot of light, maybe it's just going to completely melt and self-destruct. And you need it to be light, of course, because if it's heavier, it's going to take a lot longer to get there. So I think that I'm not holding my breath that effort will be successful in what they're planning. But for sure, the effort is going to drive lots of really interesting technological improvements in lasers, in light sail technology. Maybe that this sort of technology will be useful for something less ambitious than trying to go to another star system with another planet, with an actual planet at it. But it's, kudos for people to dream big. You can't fault that. And you know what? You could go back and start thinking about, well, Christopher Columbus or the other explorers even before Christopher Columbus saying that they were going to go head off to find that land across this big body of water. I'm sure there's lots of people saying, yeah, I don't think that's going to work. So maybe that effort will prove us wrong.
Yeah, I think dreaming big is a really good, and just like the appreciation of how much kind of spin-off applications things have. That being said, I think along all of that discussion of breakthrough starshot was Pietro. I physically heard him shift in his seat when you mentioned basketball. And so I think him and the other speakers are itching to come on. So what I want to do first is I'm going to do the reveals of trivia, and then I'll let all the speakers come back, and we'll do like a last kind of shout out before the end. But Pietro, I know you're so excited to be able to talk about maybe that basketball idea a bit more. But James, I want to thank you again, and let's find out about trivia. I've been told that my helpful friend Nick has been able to go through and grade all the trivia in the time. So I might even be able to announce a winner tonight live, and then we'll come back. So let me share my screen. That's the wrong window. And it is time for the reveal of trivia answers. And so we had trivia round one. The question number one was, what sort of electricity do you get when you rub two balloons and they stick together? And this is static electricity. Let's go to question number two. Which planet has the largest ocean? And this is not strictly speaking an ocean like Earth has. You have to go to a very weird type of ocean that you find on Jupiter. And that is actually an ocean of hydrogen. So it's, you get rid of the oxygen, it's not needed. We have this big pool of liquid hydrogen, and that is the biggest ocean in the solar system on a planet. Alrighty, question number three. When the Mars rover Perseverance landed on Mars, how long was the delay before we knew it landed? It turns out this was 11 minutes. 11 minutes for this time. I think when we did it with Curiosity, it was closer to 7 or 8. So it all depends on exactly where the planets are at the time of the landing. But yeah, we didn't know for 11 minutes. Number 4 was name this object. And this object actually has quite the Canadian connection. It is the Atlas detector at CERN, which has a huge Canadian component. So even though it's located at CERN at the border of Switzerland and France, Canada is very involved with this detector. And basically it's a high energy particle detector for looking at the results of particle collisions. And last but not least, for round 1, was name the movie that takes place almost entirely in a lunar base and stars only one on-screen actor. And that is Moon with Sam Rockwell. Fantastic movie with the presence of another actor that does not deserve our ability to say his name. But anyway, let's go on to round 2 with the name this scientist. And like I said, I think the pipe is almost the better indicator if you know anything about this guy. But it also has another constant named after him, which leads into whether or not we have a big rip or closed universe or whatnot that Akanksha spoke of. And this is Edwin Hubble. So maybe you're familiar with the Hubble constant, which is a measure of just how fast the universe is expanding right now. All right, question 7, a movie I have not seen, is name the movie where George Clooney plays an astronaut stuck on Earth, trying to save returning astronauts who don't know what awaits them when they do return. And that movie is Midnight Sky. Not to be confused with Midnight Sun, the Edward Cullen sequel to Twilight. Midnight Sky. Question number 8. Recently, Mars has been an active spot for space research. Name the only 2 countries to successfully land a rover on Mars. And this question should have been easy because we gave you the answer during Space News tonight. And that is USA and China. And that's not to say that a lot of the experiments have lots of collaborators across the globe, not just in the US. I know that in Halifax, there's laser scientists actually using LiDAR at Dalhousie. who had their LiDAR system on even the Phoenix probe to measure the atmosphere components on Mars, but that mission was led by the US. And so the two answers are US and China. Question number 9 was, what naturally forming rock floats in water? And the answer was pumice, and indeed it is the only naturally forming rock that floats. And last but not least, question number 10 is, which planet has the shortest day-night cycle? And it's a planet we've already heard about tonight, and that is Jupiter. So my understanding is there are 3 people that all got 9 out of 10 questions correct. And Nick, I don't know if you want to comment on like, what were the, I don't know, was it close? Like, were there other 8s and 7s? You might have stepped away.
Can I just speak right now?
Yeah, okay. Go ahead. Nick behind the scenes. Come on.
Looks like, hi guys. This is Nick from behind the scenes. Yeah, there were a few people who got 7s and 8s, but it looks like there was a 3-way tie. We do not have names for 2 people. One of them gave us a name, but not an email. So Sean Garnett won, but we don't have his email. So if Sean, you could give us your email.
Sean, you messaged us on Facebook this evening, so yeah, we can get in touch with you there.
Yeah, absolutely. Then the next person who got 9 out of 10 is ZB20@queensu.ca. I wish I had a better name to refer to you as, but ZB20@queensu.ca, you will hear from us very soon. And then finally, the third person, and this is the first time we've had a 3-way tie in Astronomy on Tap Kingston, was Fitzel324@comcast.net. So these are the 3 people who won. And now I'm being told, oh no, that's it. That's good. And that's all from me. Bye-bye.
Cool, thanks a lot, Nick. So we'll be in touch with all of you. I think we'll be looking to send you probably a mug and maybe a t-shirt. And I'll be in touch with more details about that. But congratulations, thanks for engaging with trivia, and thanks for hanging out tonight. And so with no more ado, I want to bring on our speakers again. One last opportunity to thank them. And maybe here, if any of them have any questions, or we're dying to ask some of the other speakers questions that didn't have a chance. And I'm trying to think, like, Akanksha, how dependent is your research dependent at all on lasers, or do you use completely different types of technology?
Sorry, I think I missed that. Was that for me? The lasers?
Yeah. You do observations of star forming and molecular clouds and magnetic fields. And so I'm trying to think, like, does adaptive optics come into play for doing those kind of observations? Or do you rely on very different types of technology to detect those?
Yeah, that's a good question. So to see for star formation, you want to look at the sub-millimeter and infrared range. And a lot of that is blocked by the atmosphere. I'm not sure how much adaptive optics would help, but we do like to go above the Earth's atmosphere. So either using like balloon telescopes, so you can have going above the Earth's atmosphere, or airplanes like the Sophia telescope to go above the Earth's atmosphere. These are sort of the more cheaper, accessible alternatives. And then, of course, there are the space-based telescopes to get that sub-millimeter and infrared light that's useful in star formation. I haven't really used too much adaptive optics with lasers yet, but maybe that's also there.
It's kind of interesting why, like, I guess you were saying, James, about how some of the atmosphere doesn't let in some of the electromagnetic spectrum. So adaptive optics really just plays a role in certain wavelengths of observations, and others it really doesn't have any ability to kind of help us out. Is that a good way to think about that?
So certainly, if I wouldn't know if, I'd assume with even a spaceborne telescope, you're getting up nice and clear. There's not much absorption, so there's not going to be if you think about it, absorption and the bending I was sort of hand waving through, it's all related to the same sort of thing. So if there's no absorption, there's not going to be much bending. I did want to ask Pietro a question, because I still got this image of that poor scientist working in a lab in a galaxy that there's no dark matter. Are you saying that right now there could be no dark matter in our solar system?
So we actually have reason to believe that there is dark matter in our around us. There are even people that have measured what is believed to be an excess at the center of a galaxy. So we do think we have enough observation and measurement to think that there is a local density, with even some constraints on properties such as the velocity at which some of those particles are moving around us, or things like this. But obviously, being a little bit of sides here, until I see a direct evidence of measurement, will kind of say what we observed, but it'd be nicer to see a real direct collision with one of those particles on.
And I was wondering, Pietro, why does the galaxy not have any dark matter? Like, why is that even something that's possible? I'm so used to thinking, like, when you have that plot of all the different graphs, sure, I could appreciate that they're a bit different, but like for somebody to have like none, it just seems really unique. Like, why does that get to be?
Right, and that's why it was so hard actually to find them. The first observation of a rotation curves of galaxy without dark matter came in 2018. So this is not an easy thing to observe and to look for. And really, to answer that question on why that happens, we would have to better understand the very early stages of the universe, the post-bounce from the Big Bang. And now some of those galaxies started expanding, some of the matter expansion in the early stages, perhaps even just before the Dark Ages. So we don't have yet that much information to do that, but the best coherent picture that we can put in is that as matter started isotropically expanding, some dark matter went in there and some dark matter didn't.
There's a question from the audience, which is like, what's the next steps in technology development for dark matter detection?
But that is a brilliant question. So without getting too technical, obviously, in the field of direct detection, I feel like we are currently going in two different directions. So there are people that are focusing more on what we call heavier candidates of dark matter. So dark matter that tends to be a little bit more bigger in mass. And so there, the technological challenge is building larger and larger scale detectors, entering into the hundreds of ton scales of detector that have very low radioactivity entry, capable of measuring, instance of light at an infinitesimal precision. However, there are a lot of people that are going also in another direction, which is they're looking for lighter and lighter dark matter candidates, so dark matter particles that are a little lighter in mass, so that they weigh a little less. And in that field is sort of eating up right now, and there's a lot of new technology that are entering as a possibility, from superfluid helium being readopted for direct detection, to even quantum computing and qubits being now considered for possible low mass dark matter searches.
So maybe we have time for just one more question. I don't know if there was any other questions between you guys.
I did have a quick question for James. So the Nobel Prize that was won by Donna Strickland, I don't know if you remember this. Can you maybe just explain what was the significance of her work, if you know? If not, I don't.
Yeah, and I was so excited when that announcement came out. I mean, it was just so neat. Professor Strickland is just this great person who represents us scientists so well. So she has this really neat story about how she started as a PhD student and was just attracted to a lab where they could create many beautiful colors. So she was, in a way, your talk, the artistic meshed with the science. That was really what engaged her. And what she solved this problem that has reoccurred, that if you take a pulse and you amplify it, we can do that so it gets more and more energy. The problem is you amplify it so much that it actually starts destroying the amplifier. And her trick was to take the pulse, and before amplifying it so that it got too high intensity, she stretched it out in time so that the peak intensity went down, and stretched it out by like a factor of 10,000, then amplified it, and then very carefully put it back all on top of each other outside of the amplifier. And so she just blew away all the records at the time at what sort of intensities a light pulse could have. And now these pulses are routine. Certain aspects of laser eye surgery just makes use of this technology off the shelf. And so she's really, I mean, had this sort of huge impact. Another interesting thing, I don't want to bore people too much, but you gave me the opening. It's a case of trying to anticipate what discoveries will have the impact. She put this result, her and her collaborator put this result in a journal that was relatively low impact, but it's, you know, in terms of people realizing how important it was, it just got bigger and bigger and bigger, and opened up whole new areas of research because it was now this new tool. If you think about it in terms of, if you can make a hammer, that's pretty good. But if you can make a hammer that's 1,000 times bigger, well, then you can hammer in a lot more than just little nails.
Cool. Well, I think that's enough time for tonight. I really want to thank all of you for your fantastic talks, for hanging out with me and with everybody at home. Really, really, really great hearing from all of you. And thank you again. And thanks to everybody at home tuning in. I know we're hoping to come back with you in the end of August for maybe our next Astronomy on Tap. So have a fantastic summer and be safe. And we'll see you again. Ciao, and thank you.